Hineh מה213 שבטחים גם יחד. Hineh מה213 שבטחים גם יחד. Hineh מה2, Hineh מה2.
So we want to look at 5 examples on partial derivative. And the first one says find the partial derivative of z with respect to the dependent variable x and y. So that means we want to find the partial derivative of z with respect to x and partial derivative of z with respect to y. So the first question says x squared plus y squared plus z squared is equal to 25. So I will differentiate with respect to x, differentiating with respect to x. This is what I am going to have when I differentiate with respect to x. So what happens is that you will keep y constant. Anything different from z and different from s will be kept as constant. So differentiate s squared, the answer will be 2s, plus differentiate y, the answer is 0, plus differentiate z, the answer will be 2z. But don't forget, z is the function of x and y, so the independent variable are x and y. So because I have differentiated z, I will add the z, the s, so it's equal to 0. Whenever you differentiate a constant, the answer is 0. So this y as well is like a constant here because I'm only concerned with z and x. So I'll bring 2s to the other side so that I will have 2z, the z, the s to be equal to minus 2s. Divide both sides by 2s. At the end of the day, you get the z ds to be equal to minus x over z. So I'm done with the first example. Now let us differentiate with respect to y. S squared plus y squared plus z squared is equal to 25. So with respect to y now, differentiating with respect to y. So I have anywhere you see s, this one will be 0 now because it's now a constant, plus this one will be 2y plus 2z. Obviously I'm just doing normal differentiation. Then this one will be z dy is equal to 0. So again I will have 2z dz dy to be equal to minus 2y. Now divide both sides by 2z, dz dy will eventually be equal to minus y over z. So the first question 1a, that is the answer to question number 1a. Now let us go to 1b. 1b question is having s square open bracket 2y plus 3z, then plus y square open bracket 3x minus 4z plus z square open bracket s minus 2y is equal to xyz. We are going to first open the bracket. I have 2s square y plus 3s square z plus 3sy square minus 4y square z plus sz square minus 2yz square to be equal to xyz. Differentiating with respect to x, so I will take y to be constant, so I'm only interested in s, so that means I'm only going to be differentiating this and this because it's this one. So Anyone different from what I have underlined will be kept as constant. So this one now, 2y is like a constant. Now differentiate s squared. The answer will be 2s plus. Now look at this one. Open a bracket for it. Differentiate s squared. You keep the rest as constant. This is 3z. 3z. Differentiate s squared. The answer is 2s. Don't go yet. Now keep the s square now, or keep the 3s square. 3s square. Differentiate z. The answer is 1, but you must write z ds because z is there is the dependent variable. Plus, now the next one, differentiate x here. You will have just 3y square because if you differentiate s, the answer is 1, and every other thing will be constant. Now minus, there is no x here, but it's just z. Differentiate z, the answer is 1, so I will just have minus 4y square. But don't forget, I have differentiated z. Whenever you differentiate z, you have to put the z, the x, or the z, the y, depending on what you are differentiating with respect to. So I will have minus 4y squared z dx. Now plus, this is also part of what I will differentiate. Now plus, differentiate the x here, the answer is 1. 1 times z square is this z square. Plus, now I'm still on this. Differentiate z square, the answer is 2z. So you have 2sz dz ds because I have differentiated z. Now, what I'm going to have next will be minus, differentiate this one, z squared, the answer is 2z. So this one will give me minus 4y z dz ds to be equal to, I will differentiate with respect to s. The answer will give me, if you differentiate s, the answer is 1. Then I will have 1 times yz will give me yz plus, differentiate with respect to z as well, the answer is 1. So you have xy dz ds. Now let me first simplify it before I collect like terms. So I have 4xy, then this one 3 times 2 6 plus 6sz, then this one plus 3s square dz dx plus 3y square minus 4y square dz dx. Then I have plus z square plus 2sz dz ds minus 4yz dz ds is equal to yz plus sy dz ds. Now what I'm going to do is that I am going to bring everyone that have the zds to one side and factorize them. This one, this, and this. I'm going to factorize all these ones. So when I factorize them and I bring them to the left hand side, I'm going to have 3s square plus minus 4y square. So this is what I am picking, 3s square dz minus 4y square dz plus 2sz dz plus 2sz dz minus 4yz dz. Then this is xy dz. Bring it to the other side, it becomes minus xy dz. So the zds is common in everything, so I just factorize immediately. It's equal to, now what are you left with? I'm left with yz yz is already at the left hand side. This is what I'm left with, yz, which is already at the left hand side. I'm left with yz, left with this, 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 and that's all. So I have yz, so that's the first thing here, minus, since it's coming to the other side, minus 4xy minus 6xz minus 3y square minus z square, and that's all. So at the end of the day, what I'm left to do is just to divide both sides by the coefficient of ZDS, so that at the end of the day, or finally, I will obtain the ZDS to be equal to yz minus 4xy minus 6xz minus 3y square minus z square all over 3s square minus 4y square plus 2sz minus 4yz minus xy, and that's the answer. Let us take the partial derivative with respect to y. Now, I'm still going to make use of what I expanded here already, but now I'll be differentiating with respect to y. So differentiate this with respect to y. Wherever you see y, that is what you are going to use. Other ones are constant. So if you differentiate y here, the answer is 1. So this will become 2x squared. That's what you have. Now this is 3x squared z. There is no y, but there is z. So differentiate z, the answer is also 1. So that's plus 3x squared. But don't forget, you differentiated z, so you have the z dy. Now plus differentiate y, this is 6xy. So minus, you have two things here, minus 4y squared z. So look at what will happen. You differentiate with respect to y, you differentiate with respect to z. So this is minus. Now, differentiate with respect to y, that means 4z will be kept as constant. Differentiate y squared, the answer is 2y plus, let y squared be kept as constant. Differentiate 4z, the answer is 4, but you just differentiated z, you put the z dy. Now to the next one, I have xz squared, that's plus z. I will differentiate with respect to z, this is 2sz the z dy. Now minus, differentiate with respect to y, that is minus 2z squared. Differentiate with respect to z as well, that will help us to get 4yz the z dy to be equal to, now differentiate with respect to y, you have xz. Differentiate with respect to z, you have xy the z dy. So bring or let us also open the bracket and expand before we get our final answer. This will become 2s squared plus 3s squared z dy minus 6xy minus 8yz. If you open 4 times 2 is 8yz, then minus 4y squared z dy. Then I have a plus 2xz z dy plus 2sz z dy. Then open this bracket, I have minus 2z squared minus 4y yz dz dy to be equal to sz plus sy dz dy. Now collect like terms, bring all z dy to the left hand side and let other ones go to the right hand side. So in reality, all this one will remain at the left hand side, all these ones, then this one, then this one will come to the left hand side, and the rest we have to go to the right hand side. So I have 3x squared, right, minus 4y squared, that's what I have, plus 2sz, then I have minus 4yz, then bring this one to the other side, that's minus xy dz. So that's all. So after that I will close the bracket. So close the bracket so that I have dz dy, then to be equal to, now sz is already here, sz, then bring the rest to the other side. I have sz minus, let me write it here, minus 2s squared. Don't forget they are coming to the other side, so the sign will change. Minus 2s squared plus 6xy plus 8yz, so then plus 2z squared. At the end of the day, make the z dy the subject, so divide both sides by the coefficient of the z dy. I have the z dy to be equal to sz minus 2s squared plus 6xy plus 8yz plus 2z squared, everything over 3s squared minus 4y squared plus 2sz minus 4yz minus xy, and that is the answer to that question. So in reality, before we go to the next question, this is plus 6xy, but here is supposed to be plus, so that's an omission. Please correct that. This is plus. So where do I have it next again? So by the time it comes to the other side, it's supposed to be minus, so I will put minus there. So remove this plus and put minus 6xy minus 6xy, so that at the end of the day, in my final answer, we will have minus 6xy minus 6xy, and that's all. Let us go to the next question. The second question says that if z is equal to x dz dy dx plus y dz dx is equal to we should show that x dz dx plus y dz dx dz dy, not x, this is supposed to be y dz dy, to be equal to minus 2z 1 plus z. Now the first thing you need to take note of is that z is equal to 1 over x squared plus y squared minus 1. In other words, if I want to write this in indices form, this will become x squared plus y squared minus 1 raised to the power of minus 1. It's still the same thing from the law of indices. Now, if I square z, I have z squared to be equal to 1 over, I have x squared plus y squared minus 1 all squared. So 1 square is actually 1. That's why you see me still write 1. I should have squared everything, but 1 square will still give me 1. So this is also equal to x squared plus y square minus 1 raised to the power of negative 2. So I'm getting to a point, that's why I'm showing you this. Now again, from this z equal to 1 over s square plus y square minus 1. If you reciprocate or cross multiply, this will become z will be multiplying s square plus y square minus 1 to be equal to 1. So all this will be very useful as we want to prove this. Now I have z to be equal to s square plus y square minus 1 raised to the power of negative 1. Differentiate z with respect to x. So the z ds, look at what will happen here. The power here is minus 1. It will come down minus 1. Then you have s square plus y square minus 1. Now you will just the law of indices. Then you will subtract 1 from here. Minus 1 minus 1. Multiply by differentiate what is inside. So there are two ways to solving this. It's either you use what we call the chain rule. The chain rule, that means it will let you to be s square plus y square minus 1. So at the end of the day, the z dx will just be equal to the z du multiplied by the u dx. So this one can help you. You can use chain rule to do this and you will arrive at the same answer. But if you don't want to use chain rule, look at what I'm doing here. I have s square plus y square minus 1 raised to the power of negative 1. So by the time you differentiate, don't forget, if y is equal to s raised to power n and you are told to differentiate, y prime will be what? The power will come down, nx, and then you subtract 1 from the power. That's how we solve, or that's how we differentiate. So that's what I'm also using here. The power is negative 1 minus 1. Then I have s square plus y square minus 1. Then I have minus 1. Then subtract 1 from the power. That's not all. The remaining thing is that differentiate what is inside the bracket. We will now differentiate this. So don't forget, I am differentiating with respect to s. Every other variable will be kept as constant. So differentiate s squared, the answer is 2x. The answer is 2x, as you can see. If you differentiate y squared, the answer will be 0 because I am not differentiating with respect to y. If you differentiate 1 is obviously a constant. The answer will be 0. So at the end of the day, the z ds will be equal to minus 2x. Then I have s square plus y square minus 1 raised to the power of negative 2. So because minus 1 will give me minus 2. So this will eventually become minus 2x. Now all these ones, look at it, s square plus y square minus 1 raised to the power of minus 2 is exactly z square. S square plus y square minus 1 raised to the power of minus 2 is z square. So all this s square plus y square minus 1 raised to the power of minus 2 will give me z square. That's the first one. Now let us differentiate with respect to y. Now I have the z, the y to be equal to, if you look at this one again, that's what I'm using. I have a minus 1 s square, that's the power, bring the power down, minus 1 s square plus y square minus 1 raised to the power of minus 2, because at the end of the day you will do negative 1, negative 1, it will give you negative 2, multiply by, differentiate what is inside the bracket, differentiate x, the answer is 0 because now I am differentiating with respect to y. Differentiate y square, the answer is 2y. Differentiate 1 is a constant, so the answer will be 0. So at the end of the day, this one will also give me minus 2y, because minus 1 times 2y will give me minus 2y, open bracket, s square plus y square minus 1 raised to the power of negative 2. So this will be equal to minus 2y z squared. Now let us come to look at what we want to do. Show that s dz dy dx plus y dz dy is equal to this. That is what we want to show now. Start from the left hand side. Do not write the right hand side, just start from the left hand side. You have s dz ds plus y dz dy. So this is s multiplying dz ds. This is what I obtain, minus 2s z squared. That is what I obtain. Then plus y dz dy, I obtain minus 2y z squared. So open this bracket, you have minus 2s squared z squared, then minus 2y squared z squared. So at the end of the day, see what is going to happen. Minus 2 is common. In fact, minus 2z squared is common. So you will be left with s squared plus y squared. That is what you are going to be left with. Now look at what will happen here. In the bracket, look at what I'm going to do now. So inside the bracket, I'll introduce something. I have minus 2z all square, open bracket. I will have s square plus y square minus 1 plus 1. Minus 1 plus 1 will give me 0, so I have not changed anything. Why am I introducing minus 1 plus 1? Because I want it to look exactly like this. S square plus y square minus 1. So look at what will happen eventually. This is minus 2. This is z square. Z square means there are two z. Z times z square. So I'll just take 1. The second one, I'll use it to multiply what is here. So look at it. Z times z will give me this z square. Now what is in the bracket? I have s square plus y square minus 1 plus z times 1. So in reality, I use one of the z to multiply what is in the bracket. So I use one of the z to multiply this s square plus y square minus 1. Then this one is still there. So that's why I have z times 1. So whenever something is outside the bracket, you use to multiply everything in the bracket. So eventually, or at the end of the day, I will have minus 2z open bracket. Now z multiplied by s square plus y square minus 1, the answer will give me 1. Z multiplied by s square plus y square minus 1, the answer will give me 1 plus z times 1, the answer is z. So, and that is what we are told to prove from the question. Let's go to the next question. So look at this question number 3. Find all the second partial derivative of z if z is equal to x squared plus 3xy plus y squared. Now the problem here is that some people don't know what they mean by all second partial derivative, but in this example you will see how we are going to do it. I have z to be equal to s squared plus 3xy plus y squared. So look at the first thing I'm going to do. Differentiate with respect to s. The z partial derivative with respect to x will be equal to differentiate x squared. The answer is 2s plus differentiate x here. Don't forget y will be kept as constant. Differentiate x here. The answer is 1. So you will be left with 3y. Differentiate x here. There is no s. This is a constant. So the answer is 0. Now find the second partial derivative. The square z over the s square. The answer here will be 2, and that's all. This is the second partial derivative. Now let's go to y. I have dz dy. This will be equal to differentiate to, that means I'm differentiating with respect to y. This one will be 0. This one will be 3x plus 2y. Now take the second derivative, this square z over the y square. The answer will be 2 as well because this one does not have y. The answer is 0 if you differentiate this with respect to y. If you differentiate 2y, the answer is 2. So that is not all. I just look for 2 of the second partial derivative. Now I want to find the square z over the s, the y. So this the s, the y means you will first differentiate with respect to s, or in other words, it means d dx of the z dy. So that means the z dy is what? 3s plus 2y. Now this is the z dy, 3s plus 2y. Differentiate it with respect to s. If you differentiate, that means d ds of the z dy is what? 3x plus 2y. What this one is trying to say is that what is in this bracket, differentiate it with respect to s, the answer will be 3. And again, we'll do this square z all over the y, the s. I have the square, or this is otherwise d dy of the z ds. So this is d dy. The z ds is 2x plus 3y. 2x plus 3y. So if we differentiate this with respect to y, the answer will be 3. And that's all for this question. So let's take a minute or two for a period of short break.
שבטחים גם יחד, הנה מה טוב, הנה מה טוב, לילה 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 לילה, הנה מה טוב, הנה מה טוב, לילה 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 לילה.
So it's okay. Let's continue now. 4a, obtain all these. The phi, the s, the phi, the y. This is supposed to be y. The square phi over the s square. The square phi over the y square. The square phi over the s, the y, for each of the following. Now, the first question, phi is equal to ax plus b over y plus cy over x. I can rewrite this as as plus by raised to power minus 1 from the law of indices plus cy s raised to power of minus 1. Now we are going to find all these. Now the first thing, the phi, the s, that means differentiate with respect to x. If you differentiate as, you have a. This one does not have s, so the answer is 0. Differentiate s here. Don't forget, you just focus on x. The power of x here is minus 1, so the power will come down to become minus cy s raised to the power of minus 2. Of course, you understand that you will subtract 1 from the power. So minus 1 will give me minus 2. So that this will just be a minus cy all over s squared. That is the phi, the s. Now, the phi, the y, differentiate with respect to y. The implication is that differentiate with respect to y. This one will be 0. Then this one will be minus b y raised to power minus 2. If we differentiate y here, the answer is 1. So plus cs raised to power minus 1. So this will become minus b over y square uh, plus c over s. That is the answer. Now, the third one, we want to do this square phi over the s square. This square phi over the s square. So that means this is the phi ds. I will differentiate this the second time with respect to x. If you differentiate this, a is a constant, it will give me 0. Differentiate this one will become minus 2 cys raised to the power of minus 3. So this one will give me 2 cy all over s cube. That is the answer for that question. Now, I'm not done. We are left with two things to find: this square phi over the y square. Now differentiate this side the second time as well with respect to y. This will also become minus 2b y raised to the power of minus 3. So the answer is 2b all over y raised to the power 3. So, and the last one, this square phi all over the s, the y, the s, the y. So this one means go to the phi dy, then differentiate this with respect to s. Differentiate this one the second time, but now with respect to s. So this one will become, by the time you do that, this is it. If you differentiate this one with respect to s, this one will become 0 because it does not have x. Now this one will become minus c s raised to the power of minus 2. So this is minus c over s square. That is the answer I'm going to have in this case. So I am done with the first question. Now let's go to the second one. The B part says phi is equal to xy sine xy. Now differentiate with respect to s. Now this is looking like product rule. So whenever you are differentiating this one will serve as your u, this will serve as v. And what is product rule? U dv ds plus v du ds. So this is what I'm going to be using. Just have this at the back of your mind and we'll be differentiating directly. Now the phi ds, this will be equal to, now don't forget, I will be differentiating with respect to x. Y will be a constant. So I have xy, that is u. Differentiate sine xy. When you differentiate xy with respect to s, it's like differentiating sine 3s. If you differentiate sine 3s, you differentiate 3s, the answer will be 3. Then you have cos 3s. Same thing. Differentiate sine xy, you have y cos sy. That's what we are going to have. Plus now v, that's sine xy, multiplying, differentiate s here. If you differentiate s, the answer is 1. 1 times y. So that at the end of the day you have xy square cos sy plus y sine sy. That is for the u, the phi, the s. Now the phi, the y, this will also be equal to, now I'm differentiating with respect to y, u, that's sy. Differentiate sine xy with respect to y. Differentiate xy. If you differentiate y, the answer is 1. 1 times s. So I will have s. If you differentiate sine, you will have cos. S cos sy. That's what you have. Plus now v. I have sine sy. Differentiate with respect to y. You will be left x. So that I have s square y cos sy plus s sine sy. That is the answer to the second question. Now we want to differentiate the second time now. This square phi all over the s square. So that means the answer I have here, I am going to differentiate this the second time with respect to s. I'm going to differentiate this with respect to s. Don't forget, in this case, this will be serving as uv. But this one, there is no problem here because the y is a constant. Since I am differentiating with respect to s, so I have sy square. Differentiate this cos xy. If you differentiate xy, you will be left with y, because when you differentiate s, you have 1. 1 times y will give me y. And if you differentiate cos, the answer is minus sine. So I will have minus y sine xy. That's what I'm going to have. Close the bracket, plus. Now v, that's cos sy. Differentiate this with respect to x. The answer will be y squared. Do not multiply this y square with the argument or with the angle. It should always be at the back of the theta, whether cos or sine. So I have cos xy y square. That's not all. This one is still there. Plus differentiate y sine sy. I've told you before, y is a constant. I will just have y here. Differentiate sine sy with respect to x. If you differentiate xy, the answer will be y. So that this one will become y square. Then differentiate sine, the answer will become cos sy. So that at the end of the day, this will be equal to minus sy cube sine sy. Then this one will become plus y square cos sy plus another y square cos sy. So this will give me minus sy cube sine xy. Y square cos sy plus y square cos sy. This will give me 2y square cos sy. And that's the answer to that question. Now let's go to the third one. We want to do the square phi over the y square. The square phi over the y square. Now I will differentiate this with respect to y. This is u, this is v. Product rule will be useful in this place. So this will give me uv sy square. Differentiate cos, the answer is minus sine. Differentiate xy with respect to y, the answer is s. So I will have minus s sine xy. That's what I'm going to have. Plus cos sy. Differentiate this with respect to y, the answer will be s squared. That is what the answer will become. Now plus, this is s. It's a constant because we are differentiating with respect to y. Differentiate sine, you have cos. Differentiate sy, you have s. So that's one. You now have s multiplied by this s that is existing here before it become s square cos sy. So that at the end of the day, this will give me minus s. So this is not sy square, it's s square y. This is s square y cos. So this one will give me minus s cube y sine xy plus s square cos sy plus s square cos sy, so that this will become minus s cube y sine sy plus 2s square cos sy. Now the last question here, we want to find this square phi all over the s, the y. So that means I'll go to the phi, the y. This is it. This is the phi, the y, s square y cos xy plus s sine xy. I am going to differentiate this with respect to x. So that means product rule will be useful here. Product rule will also be useful in the second term as well. So now this is s square y. Now differentiate cos sy with respect to x. The answer will give me minus y sine xy. That is what I'm going to obtain. Plus now v is cos sy, the u ds. Now differentiate this with respect to x. The answer will give me 2xy. That's what the answer will give me. Plus this one, different u is, that's x. Differentiate sine xy with respect to s. The answer will give me y cos sy. So I have y cos sy. That's what I'm going to have. Plus I have sine sy. Differentiate x. The answer is 1. So that at the end of the day, this will be equal to minus s square y square sine xy plus 2sy cos sy plus sy cos sy plus sine sy. So the final answer will now become minus s square y square sine sy plus 3xy cos sy plus sine sy. This is the final answer. If 0 raised to power 3 minus sz minus y equals 0, prove that the square z over the s, the y equal minus 3z square plus x all over 3z square plus 3z square minus s raised to power 3. Now I have z raised to power 3 minus sz minus y to be equal to 0. So now differentiate with respect to s. So this z raised to power 3, it will become 3z square dz ds minus, if you differentiate x here, the answer is 1. 1 times z plus now if you differentiate z, the answer is 1. 1 times s, but don't forget, whenever you differentiate z, you must put z ds minus 0. So this one is 0, is a constant, so the answer will be equal to 0. Now I have 3z square dz ds minus z minus s dz ds is equal to 0. Now factorize the z ds. I will be left with 3z square minus s dz ds. Now this one will come to the other side to become z. So when it's so we will now make z ds the subject of formula. The z ds will now be equal to z over 3z square minus s. That is the answer to the first. That is the first thing you need to obtain. Let's call it 1. Now, differentiate with respect to y. Now, with respect to y, let us see what we are going to obtain. This will still become 3z squared, but now it will become dz dy. Now, this s is a constant, so I'll just be left with minus s dz dy. If you differentiate z, the answer is 1. 1 times s, s. But whenever you differentiate z, you will have to put dz dy. Differentiate y, the answer is 1, so it's equal to 0. Make dz dy the subject of formula. This one will become 3z squared minus x dz dy is equal to 1. So dz dy is equal to 1 over 3z squared minus x. That is what we are going to obtain. Now, this is what I have. We will now differentiate this with respect to s. Differentiate with respect to s. Why am I differentiating with respect to s? That is what we want to prove. The square z over the s dy. So this one will become, now I'm going to be using quotient rule. This is u, this is v. Don't forget quotient rule says v du ds minus u dv ds all over v squared. That is what quotient rule says. So this one will become the square z over the s, the y, to be equal to v is what? Now I'm following this rule, quotient rule. This one will become 3z squared minus s multiplied by the u ds. You know, u is 1. Whenever you differentiate a constant, the answer is 0. Minus u is 1. Now dv dx. Now differentiate what is at the denominator. So differentiate 3s squared, you have 6z, but you are differentiating z, so you have to write dz ds minus differentiate x, the answer is 1. Don't forget we are differentiating with respect to s, all over v squared. So this is 3z squared minus s all squared. That is what we are going to have. Now, anything multiplied by 0 is 0. So I'll be left with this. This one will become minus 6z dz ds. But what is dz ds? I know what dz ds is already. That is what I first look for. Dz ds is z all over 3z squared minus x. So I'm going to replace it here instead of writing it again. So this will become z all over 3z squared minus s. Then minus times minus will give me plus. That's plus 1. Everything over 3z squared minus s all squared. This will be equal to, open this bracket, this will become minus 6z squared all over 3z squared minus s plus 1. That's at the numerator, all over 3z squared minus s all squared. Now you take the LCM at the numerator. By the time you take the LCM at the numerator, you will have 3z squared minus x. This one divided by this will give me 1. So I will have minus 6z squared plus, this is just over 1. 3z squared minus s divide 1. You still give me the same thing. Multiply by 1. I have 3z squared minus s. Don't forget everything is still over 3z squared minus s all squared. By the time you simplify the numerator here, this one will give me 3 minus 3z squared minus 6z squared plus 3z squared will give me minus 3. Then I have minus 1 minus x all over. Now this 3z squared will also come down by the time you do the simplification. When you have A over B, everything divided C. At the end of the day, it becomes A over B divided by C. By the time the division change to multiplication, you have A over B times 1 over C. So you eventually have A over BC. The point is that whenever you have something like this, the numerator will come down. That's by simplification to become BC. So this 3z square minus x multiplied by 3z square minus x all square, it will become 3z square minus x raised to power 3. So minus is common and the numerator factorize it, so you will be left with minus 3z square plus s all over 3z square minus s raised to power 3. And that is all. We have proved what they want us to get. Thank you very much.